All right, example 7. It says differentiate each of the following functions and then show they have equivalent derivatives. All right, so walking up to this one, you see 1 minus cosine over sine. Our mantra now is simplify early and often, okay? Can I call 1 minus cosine of x sine of x and then divide out the sine of x's and say it's 1? No, because that only works if it's 1 minus cosine squared, and then I have to call it sine squared. So I think I'll just jump in and take the derivative using the Hody-High rule. But wait, what would you do instead? Flip. Oh, I see what you're saying. You want to bring the sine to the top and call it cosecant, which would be fine. And then when you distribute, you're going to get cosecant of x minus, and of course, cosine times cosecant is the same as cotangent. That's kind of what we're doing over here on part B. Yeah. Yeah, okay. Oh, sweet. Oh, I wanted to show you that the derivatives are going to be equivalent. So they are equivalent expressions. Yeah, okay. Now it's anticlimactic, everybody. So I'm going to use the Hody-High rule over here. So Ho is sine of x. D-high is 0. And, of course, then the derivative of negative cosine of x is what? Positive sine of x, right, because cosine generates a negative, which times the negative there makes it positive. So there's Hody-High minus high, and then D-ho is cosine, all over ho-ho, which is sine squared. Now there's nothing common in the top, so I'll just expand it. I get sine squared of x, and now I'm distributing a negative cosine. So here's again where we have to be careful. I get negative cosine of x, and that becomes a plus cosine squared all over sine squared. Now, do these divide out right there? I wrote them directly underneath each other, so or above and below each other. Does that make it cancelable by doing that? No, it doesn't. That's a term in the top. But what do we see in the numerator again? Papa Pib. Okay, by the associative property of addition, we can replace that with a 1, and we're left with 1 minus cosine of x all over sine squared of x. Yeah. And that looks a lot like what we started with, right? Very similar. We just have an extra sign in the bottom. Now, y'all saw me do that. Was that correct? Did I make a mistake today on that one? There's more we could do with that, but I'm going to hold off for now. We could start getting really crazy with some of these identities, but I want to hold off for now. So as Colin already mentioned, this is equivalent to what we started with, but this one over here doesn't require a quotient rule. By using a little trig identities, we actually rewrite this just as two terms. And we memorized yesterday the derivative of these two things. So the derivative of the left side is g prime of x. What is the derivative of cosecant? Cosecant, cotangent, but because it starts with co, it's negative, yeah? And then the next one, the derivative of cotangent, is going to be a negative something, which now turns out to a positive cosecant squared. Good. So tomorrow in your quiz, you'll have to know those. And we're pretty much done with the derivative. So in terms of finding the derivative, assuming you had these memorized, the right side was probably a little bit easier than the left side. So if you wanted to manipulate the left first to turn it into something like this, you might have an easier time with the derivative, or maybe not. If this were a multiple choice question, this is where this really would come into play. What if you were asked to find the derivative of this, and none of your answer choices were in terms of cosine and sine, but you looked at them and all of your answer choices were in terms of secant and cosecant, or cotangent and cosecant? Then you might want to simplify first, write it like that, and then take the derivative. Whereas if you were given cosecant minus cotangent, and all of your answers were in terms of sine and cosine, you might want to rewrite it first in terms of sine and cosine, and then take the derivative. It's entirely up to you. But generally, simplifying on the front end is a little bit easier than simplifying on the back end, which I want to show now. I want to show you that since these are, in fact, the exact same trig function, just in a different form, they should have equivalent derivatives, right? So let's kind of make a trig proof. Let's prove that 1 minus cosine of x over sine squared of x is actually equal to negative cosecant of x cotangent x plus cosecant squared of x. Right? This would make a great trig proof. Which side do you want to work with? You want to work with the right side and make it look like the left, or start with the left and make it look like the right? Go with the right? Okay, because we can put everything in terms of sine and cosine now. So that would be negative 1 over sine times cotangent, which is cosine over sine, and then plus cosecant is 1 over sine squared. Well, now we have negative cosine all over sine squared plus 1 over sine squared. And then since we already have a common denominator, we can just put them in the same numerator, 1 minus cosine of x all over sine squared. And there you go. Now the right side looks like the left side. Here's something else we could do. If I had asked you for this one on the test and it wasn't multiple choice, let's say your answers were in terms of sine and cosine. So you went ahead and chose to do it like this. Let's keep going with this now and see what else we could do with that, just to kind of remind you of some of the identities. I can write sine squared a la Papa Pid as what? 1 minus cosine squared. And 1 minus cosine squared is now a difference of two perfect squares, so it factors into 1 minus cosine times 1 plus cosine. And what happens with your 1 plus or 1 minus cosines? They divide out, and you're left with 1 over 1 plus cosine. So that is equivalent to what we started with. So that could be the derivative answer to 1 minus cosine over sine. They're all equivalent to each other. So trig identities. Make sure you know them. You need to know your reciprocal identities, your ratio identities, your PIDs for sure, and then we've already looked at the double angle identities this year, sine of 2x and cosine of 2x. That's pretty much the end of them. Okay? You don't need to know the composites or the half angles. Later on, there will be the power reducing, but I'll wait to throw those at you until we get there. All right, now kind of shifting gears here a little bit, we're going to look at higher order derivatives, which we kind of already have talked about in that little particle motion example. The derivative of position was velocity, and the derivative of velocity was acceleration. So acceleration ended up being the second derivative of position, and that's what we have right here. So anytime you go past the first derivative, we say you're taking a higher order derivative, second derivative, third derivative, so on and so forth. Here are some of the notations. If we start with y, then your first derivative is y prime, or dy dx, or f prime, and here's what the noun, the verb format would look like. If you're taking the second derivative, it's either y double prime or f double prime, and of course in Leibniz notation we talked about this. It's d squared y over dx squared. Your little exponents of 2's are offset. And the reason is because you're taking the derivative. Let me just show this one more time. You're taking the derivative with respect to x of the first derivative. So you're taking the verb of the noun. And notice in the top it's like d dy or d squared y over dx dx, which is dx squared. The third derivative, we go to triple prime. Leibniz notation is d cubed y over dx cubed. And of course, we've seen this already. Once you get past 3, we don't use the tick mark notation anymore. We go to Arabic numbers in parentheses. So that's the fourth derivative. That's the fourth derivative. And notice that that is not the same as this. If you read that, that's going to be the quantity f of x to the fourth, rather than the fourth derivative. So I usually stick with Leibniz notation because then we don't have those awkward parentheses around there. But so on and so forth. In general, the nth derivative is yn in parentheses, or fn in parentheses, or dny over dxn. Okay? So let's go ahead and try this out. Example 8 and example 8 and 9 deal with higher order derivatives. So here we go, example 8. If y is equal to that cubic polynomial, find that. So what is this asking us to find? The fifth derivative, right? Can we go straight from the function to the fifth derivative? No. We have to go through all the other derivatives that precede it. So when you do that, it's called a recursive generation. Recursive. You have to use the previous one to get the next one. So that means we're going to have to go through y prime, y double prime, triple prime, quadruple prime. So I'm going to use Leibniz notation here. dy dx is going to be 3x squared minus 10x to the first plus 6. Now taking the derivative of both sides again, we get d squared y over dx squared. That's the second derivative. You get 6x minus 10. Taking the derivative of both sides, you get d cubed y over d cubed, or dx cubed. And that gives you 6 minus 0. And now the fourth derivative, d4y over dx4, is 0. And once you hit 0, then what is every derivative there after that? 0, yeah. So we've already pointed this out as well in a previous example. We started with a cubic polynomial, and we hit 0 on which derivative? The fourth. So that's going to be true of any polynomial. If you have a polynomial of degree n, the n plus first derivative will be the first time you hit 0. So, on example B, we have the 57th degree polynomial that you've all grown to love, right? Everyone familiar with this guy? Probably never seen him before in your life. Yeah. It's a 57th degree polynomial, and I want to find the 58th derivative. So, here we go. The first derivative is 57 times 32. Yuck. Let's not do that. Okay. So there's got to be an easier way. And what is it? Yeah, very good. You know that if it's a 57th degree polynomial, the next derivative after that n power, the 58, is just going to equal 0. So if I'd ask you for the 100th derivative, it would also be 0. All right? Now, if I asked you for the 57th derivative, that would be a little bit harder to find, because that's going to be 32 times 57, and then that'll be to the 56th power. So then I'll multiply by the 56th power, and it'll be to the 55th power, and then times the 55th power to the 54th power. What's going to happen? It's going to be 32 times 57 what? Factorial. Yeah. That would be the 57th derivative. That's kind of a neat little pattern. We're going to be doing stuff like that at the end of the year when we get to infinite series. We'll be recognizing derivative patterns like that. But it's another nice case where the factorial shows up. All right, but the 58th derivative is 0. We just saved a whole lot of time, didn't we? Not money. That would be switching to Geico. Just time. All right, example 9. What is that asking us to do? Take the 447th derivative of sine of x. Okay. What is the second quote of the day? I finally changed the quotes. The secret of getting ahead is getting started. Thanks, Mark Twain. Whew. The journey of 1,000 miles begins with the first step. So, here we go. The first derivative of sine of x is what? Cosine. Is this one just going to be 0? Is this one of those trick questions? No, because this is not a polynomial. It doesn't expire to 0. So that is dy dx. That is dy dx. And now if I take the derivative of that, the second derivative of y with respect to x is what? What's the derivative of cosine? Negative sine of x. The third derivative is going to be negative cosine of x. The fourth derivative is sine of x. Now I'm having a little deja vu, because sine of x was what I had up here. So that was equal to the first derivative, right? So the fifth derivative should be equal to the second derivative. And the sixth derivative, wow, and the leg bone is connected to the shin bone. This is going to repeat in cycles of what? 4, just like your imaginary numbers did. So I think we pointed this out last time. Here's the easiest way to do it then. You want to figure out what the remainder is when you take 447 divided by 4. Why 4? That's the number of times it takes to get back where you started for the repeat. So let's see what that answer is going to be. 4 goes into 4 one time, you get 0. Bring down the 4, it goes in 1 time. Bring down the 7, and it goes in 1 time. And you get a 4. 7 minus 4 is remainder what? 3. So the 447th derivative should be equal to the third derivative of y with respect to x. Which, have we already found that? Yeah, it's what? Negative cosine of x. That was a time saver. Mathematicians, if they're anything, they are pattern recognizers, and then they try to make generalizations based upon those patterns. And we just did. So that's how you'll do it. Yeah.
So if you were asked that,
Mm-hmm.
you have to set it equal to the third derivative if the two are equivalent?
Well, yeah, I went through the cycle, and I went to the first time I repeated. The remainder, whatever the remainder is going to be the new derivative power.
Right. So you have to say the 447th derivative of sine of x is equivalent to the third derivative.
Oh, no, you can just say it's negative cosine of x. Yeah. I actually equated it to both of them, didn't I? Yeah, and that's fine, too. I have that the 447th derivative is equal to the third derivative, which is equal to negative cosine. Yeah. So, but you could just wipe out the middleman and just do this. That's fine. Yeah. So that one did require a little bit of work to see the repeating cycle. All right. On your mark and set, you go. You do this one. The 8675309th derivative of cosine. I'll do it with you quietly up here while I'm singing Tommy Two-Tone in my head. I heard a calculator slide open. Oh, okay. You're not doing long division on your calculator. That would take all the fun out of it. What'd y'all come up with as an answer? Negative sine of x? That's right. Yeah. When you do the old school long division here, man, it brings back some memories. Brings back memories of me doing math in a hot classroom with the windows open and the fruit flies flying around in my face and my sweat dripping onto my paper. Right? You do all that and you get a remainder of 1, so that means that it's equivalent to the first derivative, yeah, which I already have there as negative sine of x. So if I would have done that first, I would have needed to find all of those. What if you get a remainder of 0? Bless you. Then it would be equal to the fourth derivative, which is equal to the original function. What if you get a remainder of 4? Then you did your division wrong. Very good. Because it goes in a whole nother time. Right. Good. All right. So that's the trick to those. Sine and cosine repeat themselves. Sine and cosine repeat themselves. Very good. Example 10. Here's a nifty way to ask you questions. College Board loves to do this too. They give you a dearth of information about some functions, f and x, but they give you enough to answer the questions they ask you about. In this case, we have a table of values. We have values of f and f prime and g prime for two selected values of x. And based upon that, we can answer the following questions. Find h prime of 0 if h of x is equal to f divided by g. Okie dokie. Well, before we can find h prime of 0, we need to find h prime of x. So here we go. The function's names are h, f, and g. The of x you don't have to write when you're finding the derivative. So h prime is going to be the quotient rule, right? So I'm not going to write the of x. I'm just going to say it's ho, d high, that's f prime, minus high, d ho, that's g prime, all over ho squared. So gf prime minus fg prime over g squared. And now I'll plug in my value 0. So h prime of 0 is g of 0 times f prime of 0 minus f of 0 times g prime of 0 all over, I'm going to put g of 0 in parentheses and square it instead of writing it in the condensed version, g squared of 0. Is that a numeric answer? Can I walk away on a free response like that? No. I got to pull values out of the table. Now, hopefully, every value that you need for your computation will be in the table. If not, maybe something happened and you messed up. So here we go. We'll plug the values out of the table. G of 0 is 5. F prime of 0 is negative 3. Minus f of 0 is 2. G prime of 0 is negative 1. All over g of 0, which is 5, squared. So it's not difficult to pull them out of the table, but you can, by the same token, make careless mistakes rather easily as well. Is that a good place to stop on a free response? Yes. So let's go ahead and get the multiple choice answer. You get negative 15 plus 2 over 25. That gives you negative 13 25ths. You're in the hole, 13 25ths. There's the answer. Okay, now, here's kind of another little word of advice. You can go, believe it or not, straight, if you'd like, from h to h prime of 0. I realize it's a lot of extra writing, but you could do that as long as you make sure you're plugging it into both sides. Don't say h prime of x equals and then put g of 0 on that side. Bless you. I'll do that on this side over here. Find h prime of negative 1 if h of x is x times f times g. What rule are we going to use here? Product. How many factors? 3. So how many terms will I have? 3. So here's what I'm going to do. I'm going to say h prime of negative 1 is. Now I'm going to go through and I'm going to take the derivative of each one, but then instead of just saying f prime of x or g prime of x, I'm going to say f prime of negative 1, g prime of negative 1. And then I'm going to plug in a negative 1 for x. What's the derivative of x, the first factor? 1, right? You can't plug in and then take the derivative. That's the only risk of doing it this way. You got to take the derivative and then plug in. So the derivative of x is 1, and then times the other two go along for the ride. So f of negative 1, g of negative 1. Plus, now x goes along for the ride, but instead of x, I'm plugging in my negative 1. Times, now the derivative of f is f prime, but I'm going to put a negative 1 there, times g of negative 1. And then finally, the last one is going to be plus x, which is negative 1, times f of x, which is now f of negative 1, times the derivative of g is g prime of negative 1. So when you go through, make sure you're taking the derivative of the first, then the second, and then the third. And everywhere you have an x that's still visible, you're plugging in a negative 1. Now, if you're not comfortable doing that, you can do that as a second step. So you could have just said h prime is equal to 1 fg plus x times f prime g plus x f g prime. You could do that as your first step and then go to the line below that. All right, so now carefully pulling values out of the table. Do you need me to do that or do you think you got it? Well, let's just do it. I won't be able to sleep tonight, mainly because I still have sciatica in my hip, but I'll also have that unresolved feeling of not coming to a numerical conclusion here. It's like trying to sneeze and then someone messes you up right in the middle and says, "Bless you," and then you can't sneeze. And then you just got that unresolved itchy tension in your sinus cavity. And you're like, "Thanks a lot." Okay, y'all probably are done filling in while I was saying all that nonsense. F of negative 1 is 3. G of negative 1, negative 2. Good. And then it'll be minus F prime of negative 1 is 4. G of negative 1 is still negative 2. And then it becomes minus again. F of negative 1 is 3. G prime of negative 1 is 2. So there's your free response answer. And then continuing for the multiple choice, you get negative 6 plus 8 minus 6. You end up with negative 4. And there's the answer. Feels a lot better. All right. So any questions on that? Taking numerical derivatives, or taking, symbolic derivatives and then plugging in to get numerical answers. All right. Example 11, true story. True story. The position function for a falling object on or near 6 feet high on the surface of the moon. Anyone ever been there? No? Okay. Is given by this function. H of t is equal to negative 2.66 t squared plus h of o, where h of t is the height in feet at t seconds, and h of o is the initial height in feet. So we have units here, feet and seconds, seconds and feet. So question A, if you were eating at an Italian restaurant on the moon, and the Yelp review said, great food, but no atmosphere, and your meatball rolled off of the 3.2 foot high table, after how many seconds would that meatball hit the floor? Follow-up question, how fast was the meatball traveling when it hit the ground? And then follow-up story, or follow-up question, if you retrieved it within 5 seconds, would you still eat it? In other words, does the 5-second rule still apply on the moon? First things first, here's an actual photograph of 2 kids eating at that restaurant on the moon. Okay? This was taken at the Apollo 12 mission, I believe. All right. Some people say it's faked, but seeing is believing, right? There's photographic evidence. What are we going to do first? After how many seconds would it hit the floor? Like we've done before with the calculus textbook. I'm going to create my height equation. H of t is going to be negative 2.66 t squared plus h sub o. What was the initial height? It's rolling off of the table, which is 3.2 feet. So we'll put 3.2. Now I want to know how long it takes for that thing to hit the ground. So I'm going to set that equal to what? 0. And I show that right here. Negative 2.66 t squared plus 3.2 equals 0. You get checks on my exams, on AP exams, for showing the equations you're solving. Now to solve this, I'll just bring the 2.66 to the other side and then flip it around. So it's positive 2.66 t squared equals 3.2. And now I'll divide through. I get t squared equals 3.2 divided by 2.66. Now when I extract the square roots, I want to at least consider both the plus and minus. Do we want the negative one here, though? No, because we can assume that we were starting time once the meatball was on its way and not back in time. So we're just going to go with the positive square root of 3.2 over 2.66. Now that's a numeric answer. It's our final answer then for now. We need to put units on it. What are the units of t? Seconds. Okay. So it takes the meatball that long to hit the floor. Let's go ahead and pull up the calculator, because we're allowed to bring our calculator with us to the moon. Yes. So here we go. We'll just type it in. The square root of 3.2 divided by 2.66. And I'll hit enter. So on my paper, here's what I'm going to do. I'm going to put T equals. How many decimals do we report this year if it doesn't terminate? 3. And you can round or truncate. I'm a big fan of truncating. It saves mental energy. 0.96 seconds. So if you're going to use the calculator, and we'll be introducing it very slowly here, you're going to write that right there. You still report 3 decimals with unit seconds. But if you have the intention of ever using that number, you don't want to type in 1.096. Because if you ever have rounding error, if you're ever off in the third decimal, you're going to lose points. So I'm going to store that. I'm going to hit stow, which is right above on, and I'm just going to hit alpha A. Now it's in there as A if I ever need it. And if I store it as A on my calculator, I'm also going to store it as A on my paper/iPad. As long as I'm not using A somewhere else for like area, you could store it as A. And you can now refer to it as A, and it's a reminder that it's in there as A. So the next question, how fast was the meatball traveling when it hit the ground? How are we going to know that? We want the instantaneous rate of change of position. So that's the derivative of h, which is h prime of t, and I'm going to go ahead and call that v of t. This is the instantaneous velocity function on the moon. So what is the derivative of negative 2.66 t squared? Will be negative 5.32. And that would be t to the first plus 0. And now when I'm going from a variable to a plug-in, I can say either v of, and I can use my 1.096. But if I literally just type in 1.096, as I said, I could be off in the third decimal. So another good thing to do is just to put v of a. And as long as a is labeled somewhere on your paper, we'll know what you're doing. It's an intermediate step. And so now I'll go to my calculator, and I'll just type in negative 5.32 times alpha a. And I'll report 3 decimals again. That's going to be negative 5.835. If the third decimal had been a 0, you would need to report it. What are the units now of velocity? Feet per second. Good. So you would say then at 1.096 seconds, which is exactly when the meatball, or how long it was in the air, it was traveling downward at 5.83 feet per second. Okay, and then the next one. If you retrieved it within 5 seconds, would you eat it? I would hope so, because I don't know if you've ever been there. No one said they've been there before, right? The menu prices are sky high, astronomically high. You can imagine how hard it is to ship meatballs up to the moon. So because you paid dearly for it, you're going to go ahead and pick it up and eat it. Now, there might be bacteria growing on it, so you might pay dearly for eating it after the fact as well. But anyway, part B, using the given equation, determine how many times stronger the acceleration due to gravity is on Earth than it is on the moon. And since this is a true story, this should be an accurate number. How are we going to figure out the acceleration due to gravity on the moon? Very good. I could take the second derivative of my position function, which ends up being the first derivative of my velocity function, which I'll call a of t, the acceleration function on the moon for falling objects at or near 6 feet. And that's negative 5.32, and that would be what units? Feet per second squared. That's the gravitational constant, little g, on the moon. What is it for planet Earth? I'm going to put a sub n for acceleration due to gravity on the moon, and the acceleration due to gravity on Earth, a sub t. You should know it, right? Negative 32, roughly, feet per second squared. Of course, in physics, it's negative 9.8 or negative 10-ish. So now we want to figure out how many times stronger it is on the moon, on Earth than on the moon. So all I have to do is go to my calculator and go negative 32 and then divide it by my answer. So you can recall the answer by hitting second negative. I never stored that, did I? I don't need to store it. I can just recall it from the previous line. Second negative is the answer. And you get what? 5.4. Let me write it out first. The acceleration. Did I use the wrong one? That doesn't sound right to me. Which is always good to check the reasonableness of your answer. All right, I wanted to divide it by negative 5.32, which, where do I have that stored? I don't. Okay, so let's, that's a constant, right? Yeah, because I gave that to you. Yeah, I gave that to you as a constant. So let's just type it in. Acceleration due to gravity on Earth. The negatives are going to divide out. So 32 divided by 5.32. And this looks like a better number already. There we go. So that is 6.015. So on your paper, to show the calculation that you're doing, here's what I did. The acceleration due to gravity of planet Earth divided by the acceleration due to gravity on the moon, you get 6.015. Okay? So then part C, based upon your answer to part B, determine what your weight on the moon would be. Let's say after you're done eating that delicious meatball that rolled on the floor. So meatball included. All right, so you can go ahead and do yours. If you have your calculator, I'll go ahead and store this value. So, and I'll store it as X this time. We could do multiple people. So like for me, I'm not going to tell you how much I weigh on Earth, but I will tell you how much I would weigh on the moon. And this is wearing like the same spacesuit I'm wearing now, minus the heavier spacesuit. I would only weigh 38 pounds on the moon. Okay? Would that mean that my pants will fit better? No, they'll still fit the same way, but I'll be lighter. So I guess there's two ways to lose weight, right? Diet and exercise or go to the moon. Doesn't solve the clothes being too tight problem, though. Anyway, there you go. Anyone want to figure out how much you weigh on the moon? Since I have the number stored. Tyler, how much do you weigh on planet Earth? 75 pounds? 110 pounds? 110 is fat? 165. Okay. Are you calling yourself fat? That's dripping wet, right? All right. Tyler, you would weigh 27 pounds on the moon. Not bad. Not bad. You could probably bench press yourself on the moon. Yeah. All right. See how fun that is? There you go. Diet problem solved? Absolutely not. Did not solve your diet problem. It actually made it worse because the food on the moon is delicious. It's exorbitantly priced, but it's pretty delicious, so you'll eat a lot. All right, so anyway, that problem kind of represented some of the fun stuff you can have once you know the derivative and your kinematic equations. Any questions on the product or quotient rule? All right, well, we'll conclude this lesson. Go ahead and download 2.5. We'll get going with that.